Hi students, welcome to physics classes. Now we will discuss about Newton's second law of motion. In previous class we discussed Newton's first law. Now we will discuss about Newton's second law of motion. Before starting this class, watch the complete video, don't skip it, and like this video. If you like this video, it will be promoted to many users. It will be helpful for them and even helpful to me. Now Newton first law refers to Newton first law refer to external force. Net external force is 0. No net external force. What he explained in that if there is no external force, either body will be at rest or moves with uniform motion. Either body will be at rest or moves with uniform motion in straight line if no external force acts. Now in second law we will discuss about when there is a net external force. When there is some net external force. Here in real life it is possible. Everywhere force will be acting. Some net external force will be acting. So whenever net external force is acting on a body, it will accelerate. It will accelerate. So Newton's second law relates the net external force to acceleration. Net external force to acceleration. Now before entering into Newton's second law, we will discuss about momentum. Momentum is the product of mass and velocity. Momentum is the product of mass and velocity. Momentum is denoted by letter P, that is equal to mass into velocity. Now as velocity is a vector quantity, momentum also vector quantity. Now here, based on momentum, we have some examples. For example, here lightweight vehicle, for example, bike. For example, bike. And heavyweight vehicle, for example, car, are parked in a place. Now to bring them into same speed in same time, to bring them into same speed same time, so both are at rest, parked in a horizontal road. So we'll bring them into motion to particular speed. Both should have same speed and the same time. So what we should do here, we need to apply force. We should apply force for both. If we apply same force, will they come into same speed in same time? No. For heavy weight, heavy mass, for more mass you should apply more force. For more mass you should apply more force. Less mass you should apply less force. Next, if they are moving, if they are in motion, so both are moving with same speed. Second case, both are moving with the same speed. So by applying opposite force, we should bring them to rest in same time. Bring them to rest in same time. Car and bike both are moving. So by applying some external force, we should bring them into rest in same time. For which we should apply more force? Obviously more mass. Either to get into same speed or to get into rest in same time, we should apply more force for more mass, less force for less mass. So from this we can say mass is the important parameter to describe about force. We see no, for more mass we should apply more force to bring into same speed or to bring them into rest in the same time. For more mass we are applying more force. So mass is the important parameter to describe about force. Next, if you have a ball, if you throw with more speed to another person, another player, if you throw the ball with more speed to the another player, while catching he will get more hurt. It will hit no with more speed. Similarly, if you throw with less speed, it won't hurt. General, simply he can catch it. Simply he can catch it. So initially when we throw the ball with more speed, it gives more impact when compared to less speed. That means here speed is also one important parameter. Speed is also one important parameter to describe about force. If the body moving with more speed, he should apply force, more force to bring it to rest. If it is moving with less speed, he should apply less force to bring it to rest. So speed is also a parameter to describe about force. Now, as we discussed two examples, from these two examples, momentum P is the product of mass and velocity. Product of mass and velocity. Now, momentum of the body changes. When it will be changes, either mass changes or velocity changes. When mass changes or velocity changes, momentum of the body changes. To get the greater change in momentum, to get the greater change in momentum, to get the more change in momentum, so here mass velocity should change. When mass changes, force needed. Velocity changes, force needed. We should apply more force. We should apply more force. To get more change in momentum, more force is applied. Less change in momentum, less force is applied. So based on this, we can say force, momentum both are related. Force, momentum both are related. Next, one more thing, time. For example, ball is rolling. Football is rolling. If you apply more force, more change in momentum, time will be less. If you apply less force, momentum will be changes, but it takes more time. It takes more time. So if you whenever you apply more force, more change in momentum, less time. So change in time also required here. Change in time also required here. Now for example, another example we can take, when a player catching a cricket ball, it is coming from more height. So whenever taking hand, he will drag his hand back. Suddenly if he kept hands like this, what will be happen? It will hit. He will get hurt. So whenever he drags the hands, he won't get hurt. So whenever time is increasing, force will be decreases there. As he is dragging the hands, time will be more, impact time will be more, force will be reduced. Based on that also, time is required here. So from these two, we can conclude that greater the rate of change of momentum, so greater force we should apply. More change in momentum in a particular time, more force is needed. Less change in momentum in a particular time, less force is needed. Now here based on this we will take one example. Whenever two bodies of different masses, two bodies of different masses, if you apply same amount of force, if you apply same amount of force, it has more mass, it will acquire less velocity. It has less mass, it will acquire more velocity. Yes, no? Whenever you apply same amount of force for both different masses, less mass will have more velocity, more mass will have less velocity. So finally both will acquire same change in momentum, same change in momentum. So from this example we can conclude that same force is applied in same force is applied in same time, same force is applied in same time, same change in momentum, same change in momentum for different bodies. Whenever we apply same force in same time, it causes same change in momentum for different masses, same change in momentum for different masses. Masses are different but force is applied same in a particular time. Then one will acquire less velocity, one will acquire more velocity, finally product will be same. For example, if its mass is 2 kg, its mass is 3 kg, whenever force is applied it will get 6 meter per second, it will get 4 meter per second. Finally it is having more velocity, it is having less velocity. So product 2 into 6 12 kg meter per second, 3 into 4 12 kg meter per second. So whenever force is applied same, change in momentum also same for different masses. So from this we can state the Newton's second law is the rate of change in momentum, the rate of change of momentum is directly proportional to force applied on a body. Rate of change of momentum is directly proportional to force applied on a body. Whenever we apply force, on a body in the time delta t, in a time delta t on mass m, we apply a force on mass m in a time delta t. Then due to this force its velocity changed from v to v plus delta v. This much velocity is changed, delta v velocity is added because of the force. From v to v plus delta v, this much velocity is increased. Then initial momentum equal to mass into initial velocity, and the final momentum equal to mass into final velocity. Then if you do this m into v plus m into delta v, change in momentum, you can write change in momentum delta p equal to final momentum minus initial momentum, so final momentum is mv plus m delta v minus initial momentum is m into v. So plus mv minus mv gets cancelled, m into delta v is change in momentum. Change in momentum equal to mass into change in velocity. So from the statement as we discussed, rate of change in momentum is rate of change in momentum is directly proportional to force applied. From this we can write f. To remove this proportionality symbol we will take one constant k, delta p by delta t. K is a proportionality constant. Now by taking limit delta t tends to 0, delta t tends to 0 means delta p by delta t becomes dp, differentiation or derivative of momentum in time. Differentiation or derivative of momentum with respect to time. Delta p by delta t, when limit delta t tends to 0 is taken, differentiation of momentum with respect to time, differentiation of momentum with respect to time. So we can write f equal to k dp by dt. Now as we know, dp by dt is d by dt of p. dp by dt equal to d by dt of p. P I written separately. Now differentiation of momentum with respect to time, we can write d by dt. P means m into v. So mass of the body is always constant. Initial, final, in any situation, mass of the body will not change. Only velocity will be changes. So we can write this m into dv by dt. Differentiation of velocity with respect to time. We know that we discussed in kinematics, m into dv by dt becomes a. So dp by dt we can write m into a. So substitute this in the force formula. F equal to KMA. F equal to K into dp by dt, no? dp by dt becomes m into a. So F equal to K into ma. As we have K value is 1. K value 1. Then F becomes mass into acceleration. This is the formula for force. Now SI unit of force is kg meter per second square, or we can write it is kg meter second inverse square, or simply we can write Newton. Newton is a scientist name. While writing symbol we should use capital N, while writing complete name small n. While writing scientist names as a unit we have this rule. Now we'll discuss some important points related to second law. Some important points related to second law we will discuss now. Now if force applied on an object, net force, whenever we discuss force in the sense here, net force on an object is 0. Whenever net force on the object is 0, then we can say acceleration is 0. Acceleration is 0. So whenever we take this situation, second law is obviously consistent with first law. What is first law? No net force, no acceleration. Okay. Next, second law of motion is vector. Here we are discussing about force, no? So force is a vector quantity. Force is a vector quantity. It is equivalent to 3 quantities, one for each component of the vectors. Vector will be x-axis, y-axis, z-axis, I, j, k components. So it will give 3 quantities for each component of the vector. Fx in x-axis direction, Fy in y-axis direction, Fz in z-axis direction. Now Fx equal to change in momentum in x-axis direction, dpx by dt. We can write it is ma, acceleration along x-axis. Similarly, Fy equal to ma, acceleration y-axis. Fz equal to ma, z-axis. Now next one, if force is force is not parallel with velocity, if Force is not parallel with velocity, means it is making some angle with velocity, then some angle with velocity, then this force changes the component of velocity. Force changes the component of velocity along the direction of force. For example, in projectile motion we will discuss, whenever if the body is moving in a parabolic path, projectile motion, force is applied. Now velocity along x-axis, velocity along y-axis. So when the body moving in a projectile motion, in the projectile motion under the vertical gravitational force, force acting vertical gravitational force, then horizontal component of velocity unchanged, horizontal component of velocity unchanged, velocity in this direction is constant, velocity in vertical direction will changes. So force is acting in vertical direction, no, projectile motion under the vertical gravitational force, so force is acting in vertical direction, so vertical component of velocity will be changes, horizontal component will be unchanged. So we can say the component of velocity normal to the direction of force remains unchanged. The component of velocity normal to the direction of force, normal to the direction of force means perpendicular to the direction of force, remains unchanged. In the direction of force will be changes, in the direction of force will be changes. Next, whenever we consider F equal to ma, force equal to mass into acceleration for single point, for single point, F refers to net external force, F refers to net external force, and A refers to acceleration, A refers to acceleration. At the same time, if you consider F equal to ma for rigid body or system of particles, in that situation F refers to total external force, F refers to total external force, and A refers to acceleration of the system, acceleration of the system. Whenever we take single point, net external force, acceleration of the particle. Whenever you take entire system, whenever we take entire system, this force refers to total external force, and A refers to acceleration of the system. Here always F refers to external only, no internal force, no internal force in the system is included, no internal force in the system is included, no force, internal force will not include, only external force will be included, only external force will be included. Next, force applied in a certain instant of time, in a particular instant of time, it is related to acceleration in that instant of time. Whenever we apply force in a particular time interval, acceleration acquired refers to in the same interval, acceleration referred to in the same interval, and in that particular time, acceleration in that particular time, it is not includes, acceleration will not includes any previous situation, historic, initially what acceleration it will have, that will be not included here. Whatever, whenever we apply force in that situation, whenever we apply force from 10 a.m. to 10:20 a.m., if you apply force, acceleration included in this time only. Before that, what it is having acceleration will not be included. Before that, whatever it has acceleration, that will not be included. This is about Newton's second law of motion. Thank you for watching. Please subscribe for more updates.